Hi, everyone. All right, welcome. We're starting a little late, but I'll try to get through everything so you can ask me questions. So, hi, everyone. My name is Edward. I want to tell you all about what's going on with dynamic shapes in 2.1. I would love to roam around the stage, but I can't, so I'm stuck here today for the mic. All right, so dynamic shapes are everywhere in deep learning. Anytime you have an input tensor to your network where there's a dimension that may vary, that's dynamic shapes, right? So like say you're looking at the batch dimension on your tensor, and say you're performing request batching, so you're waiting for tensors to come in before you actually go ahead and run them. Well, your batch size is going to vary based on how many tensors you had in your queue. Or if your tensor represents text sequences, the length of the sequence is going to vary depending on the size of the sentence you're doing a prediction over. I talk about text sequences, and that's like a single sequence. But if you have lots of sequences, then a thing you're going to want to do is you're going to want to pack them together so you don't waste lots of memory having it padded out to the thing. And so in this packed data structure, you have an overall length of the packed dimensions, and that's also dynamic. We're all about generative AI and LLMs these days, but there are a lot of other domains that people do want to do deep learning on. And dynamic also shows up there, right? If you have recommendation systems, the number of features you have per user may vary. If you've got graph neural networks, the number of edges per nodes is going to vary. If you have object detection and segmentation, the number, height, and width of bounding boxes, that's also going to vary. So there's dynamic shapes everywhere. And of course, PyTorch made a name for itself about the flexibility of its error mode, which is mostly a way to string together a bunch of kernels. And these kernels work for any shape. It would be very bad if we had to do a separate kernel for every static shape. So when we were working on PyTorch 2, we really wanted to make sure we would maintain the charm of PyTorch 2, of PyTorch, eager PyTorch, with this level of flexibility. So last PyTorch conference, we announced prototype support for dynamic shapes. At the time 2.0 released, dynamic shapes were opt-in only with an explicit flag, and they only worked for inference. So with PyTorch 2.1, I'm happy to announce that dynamic shapes have moved to beta. So we automatically apply dynamic shapes to your model when we notice your input shapes are varying over time. In fact, you probably should stop using dynamic equals true if you don't actually need everything to be dynamic. I'll say more about that later. And we fully support training with dynamic shapes. So if you have variable batch sizes when you're feeding in data, that works as well. We've also made some progress towards supporting truly data-dependent operations like non-zero and item, although that mostly didn't make it for 2.1, so you should check out the nightlies for that stuff. It's also been super cool working on dynamic shapes to see this effort validated with happy users. We have users both inside Meta as well as in open source. In many cases, dynamic shapes weren't working quite out of the box when people wanted to do things, but we've spent a year working on all the big, complicated foundational pieces you needed, and we noticed that these days the bugs we're hitting now are relatively easy to fix. So we're hoping to hit stable soon. For the rest of this talk, I want to just talk a little bit more in detail about what's new in dynamic shapes everywhere. So I first want to talk about torch.compile, the regular eager mode experience. And then you heard all about the new export interface, and dynamic shapes was mentioned a lot there. So I want to talk a little bit about what's going on with the integration in that case. And then finally, I just want to get super technical a bit about data-dependent operations, because there is some interesting stuff going on there that I find very interesting and I want to share with you. First, torch.compile. So before I tell you about dynamic shapes, I want to mention the logging system that was also mentioned during the keynote that Michael Lazos, myself, and others have added to PyTorch 2. Traditionally, PyTorch is an eager mode library, and you don't expect a library that just has a bunch of API calls to do logging. But PyTorch 2 has this big, complicated compiler, and it's really helpful to be able to look at the logs on this compiler to understand what this complicated system is doing. So we're actually going to look at the log messages to understand whether or not dynamic shapes is working or not on programs you're doing. And so the first thing I want to talk about here is automatic dynamic shapes, because it's the most important and user-usable change to how Torch compile works when you work on PyTorch 2.1. The basic idea is that the first time we compile any piece of code, we're going to optimistically specialize all of its sizes to be static, since that's the common case in deep learning. However, if we end up having to recompile the model, any sizes that change between one run and the next, we're going to upgrade them to be dynamic and make sure we compile a kernel that will work for any size that we can handle. So here's a little example program. So it's very, very simple. We're just adding two numbers together, and then we're just going to try to run it successfully on sizes 3 by 3, 4 by 4, and then 5 by 5. And notice I didn't set dynamic equals true here, so we're going to use the normal automatic dynamic shapes. So here are the logs you're going to get. I'm going to dig into them in more detail. So on the first run, you can see some log messages, and what these messages mean isn't important, but it does mean that there's some compilation taking place. And it's very uninteresting. There's really no reasoning about dynamic shapes going on because we compiled this statically for the 3 by 3 case. On the second run, however, we see that we are creating dynamic symbols for each of the values of x.size0 and y.size0 as they changed in the original program. You can also see that PyTorch 2 is introducing a guard saying that S0 must equal S1, since otherwise we wouldn't be able to do addition on them. And on the third run, we see no log messages at all because no compilation has happened. On the second run, we compiled a kernel that works for all sizes, and so on the third run, we just go ahead and use it directly. We still support passing the dynamic keyword argument to torch.compile, but there's actually 3 modes of use now. So if you don't pass anything, you get the automatic dynamic shapes I just talked about. If you pass dynamic equals false, you get the good old-fashioned PyTorch 2 style behavior where everything is static. So this is pretty useful if you're like, no, Edward, I'm going to only call it on 5 sizes, and that's what I want. I want 5 graphs to be compiled for each of the cases. And you'll get the best performance in this way. And if you pass dynamic equals true, we're basically going to say, YOLO, everything is dynamic. Actually, this is a great way to run into bugs in dynamic shapes because everything is dynamic. And most of the time, you don't actually want everything to be dynamic. So if your code isn't working, try switching to automatic dynamic. It often helps. We also have support for fine-grained annotations on what should or shouldn't be compiled dynamically. Let's say you've got your tensor x, and x size 0 is going to be dynamic, and you don't want anything else to be dynamic, so you can't use dynamic equals true. Automatic dynamic will still work in this case, but you would waste time compiling the fully specialized static version first before you'd compile the main version of your model. So if you just annotate your tensor with mark dynamic, you'll tell PyTorch, hey, please go ahead and make this dynamic. And in fact, if PyTorch is unable to make it dynamic for some reason, maybe you're actually doing some control flow on this value, it will go ahead and tell you that this was a problem and there was a problem. And you can use maybe mark dynamic if you're just like, best effort, try it, and I don't care if it doesn't work. Conversely, you can also use mark static to force a dimension to be static, which is helpful in that case where you will know there's only 3 sizes and you want to have a copy of the graph for each size. Another cool feature, so switching gears for a moment, another cool feature we added in 2.1 is CUDA graph support for dynamic shapes. But wait, Edward, you might be saying CUDA graphs only support static shapes. And yes, that's true, but you can still use them with dynamic shapes. And the basic idea for how this works is we first compile the program, which is a pretty heavyweight process, so that you get a program that works with dynamic shapes. And then for every size you actually want to run the program on, we'll record a separate CUDA graph for each of them. Now you might think of CUDA graphs as this heavyweight thing, but they're mostly heavyweight only because you have to associate some block of CUDA memory with them stably across run to run, because they burn in all the addresses. But you can actually reuse the same block of memory for each of these CUDA graph recordings. So your overall memory usage is just the maximum usage when you had maximum batch size. This is a pretty cool mechanism, and if you're interested in learning more about how this works, you should go to Elias's session right after this one, where he's going to talk more about CUDA graph trees. So how fast are dynamic shapes in PyTorch 2.1 anyway? So here are the numbers that I pulled from 2.1 itself. The numbers you saw in the keynote were from the nightlies because we added a bunch of new we keep working on it. So these are the snapshot in time from 2.1. And you can see that, it's okay. It's a little slower to have dynamic shapes. And this is the same story for inference where, there are a little bit of different characteristics, but, it's basically the same idea. You get good performance. It is not as good as static shapes, though. There's a model-by-model breakdown on the performance dashboard, which I recommend you take a look at if you want to dig more into this. What are the sources of these gaps? There are a few explanations, but it's mostly due to Inductor's inability to specialize on input shifts when it's doing compilation. For example, reductions are normally parallelized over the individual rows being reduced. But if there aren't enough rows and the reduction dimension is large, it is profitable to split the reduction so that you have more parallel work to do. But with dynamic shapes, you don't know how big your dimensions are. You have to defer this split decision to runtime when we know the actual sizes of all the dimensions. Our current heuristic is to just take the sizes at the time we were compiling and hope that the splits work for all these sizes. But, that may lead to suboptimal decisions. Or take, for example, divisibility. Trident loads are done in tiles of 16. So if your tensor is not divisible by 16, we need extra code to mask out the invalid axes at the end of the tensor. One particularly pernicious problem is inductor's reliance on size hints on the first compilation run. If your examples are non-representative, you could end up with suboptimal choices that get applied to all of your input sizes. So make sure you warm up your models on representative input sizes. That's probably the most important. Like, if there's one takeaway you should have for how do I get good perf with dynamic shapes, warm up on the actual size that matters. The real fix that doesn't require you to do this is we should just generate multiple specialized kernels and pick the right one based on what we see at runtime. We want to do this. We've been working on a lot of other stuff, so sorry. We'll get there eventually. The way to think about PyTorch 2's dynamic shapes performance is we're starting from a compiler that supports all kinds of dynamic patterns, but sometimes doesn't generate very good code for it. So you can make your model run faster by making it more static, or you can go ahead and hope for PyTorch 2 to get better at code gen. This is in contrast to most other compilers where they're starting with a fast but static shape only compiler, and you're forced to shove your dynamic shapes problems into a statically sized box while they're rewriting their compilers to support dynamic shapes. Okay, so that's everything I wanted to say about torch.compile. Let's talk a little bit about dynamic shapes in export. Like an eager, in export, you may want to export a model with dimensions of some input tensors being dynamic. So export lets you explicitly annotate these dimensions using a MyPyTyping-like interface where you allocate a dim variable and then you say, okay, these dimensions are these dim variables. Like mark dynamic, PyTorch 2 will tell you when we don't actually manage to make the tensor export dynamic in that way. Here's an error message you might see if your exported model doesn't work with the dynamic shapes annotations. Exports will tell you, here are all the dimensions you can make dynamic, and will also tell you, here are the dimensions that are dynamic, but they have some extra constraints, like equality constraints or min-max constraints. To find out where each of the constraints came from, use the logging system I told you about earlier. Just run it while you're exporting your model. There is one thing to be careful about when working with dynamic shapes for export. There are tons of cases in PyTorch framework code where there is some special case handling for if a size is 0 or 1. For example, PyTorch relies a lot on the concept of contiguity, which says whether or not the logical elements of a tensor are laid out consecutively in memory. So, when you can get them one by one, that's contiguous, but if you have to jump, that's non-contiguous. So normally, if you take a continuous tensor and you transpose it, that makes the resulting tensor non-contiguous because you have to jump ahead n elements to get to the next element. But that's not the case when you have a size as 0 or 1. In principle, I could write some synthetic example that returns numerically different results depending on if an input tensor is contiguous or not. But in practice, all I'm doing is I just have a kernel that can only work with contiguous tensors, and I'm checking if I need to call clone before I call that kernel. The observable results are unaffected. So when we ran into this problem, we checked a number of cases, and we found the story was always the same. If you export a model assuming that the size of the dimension is greater than or equal to 2, then chances are the resulting model will also work when that size is 0 or 1. So we've enshrined this into the export user experience. When you mark a dimension as dynamic, we will always assume that it is greater than or equal to 2. It's important to know about this because you can write user code that breaks this property, i.e. just have an if statement that does one thing or something else depending on if the size is 0. If you do have a use case where this does matter, please let us know on GitHub issues. We haven't found a single case where this would actually be a problem. Okay, so for the last part of the talk, I want to talk about one particularly thorny corner of dynamic shapes, data-dependent operations like item, non-zero, and Boolean masking. This stuff, all of it didn't make the cut for 2.1. It's all on the nightlies, so there is a lot of stuff on the nightlies, so go check them out. The problem of data-dependent operations arises from relatively simple pieces of code. As an eager mode framework, PyTorch allows users to take values inside of tensors and extract them into regular Python ints, at which point they may be used for sizes or used for regular control flow. So this is a problem for a tracing framework like Dynamo, because to trace the code, we didn't know exactly which branch we're going to take in order to build a branch tree graph that we're going to compile. For ordinary conditionals, we would just look at the value to see where we went and then add a guard saying next time around the value has to be the same way. But if we have a so-called unbacked symbolic integer, which may have been the result of calling item on an arbitrarily complicated tensor computation, we can't guard on them unless we graph break after we've done the item call, at which point we do know what the size of what the value of x is. So, Dynamo supporting graph breaks means we can handle this code with a graph break. But it turns out there's lots of use cases of item that don't require graph breaks. So for example, let's suppose you're modeling a jagged tensor containing a bunch of variable length sequences. So this is back from my intro slide. It would be typical to store the lengths of the sequence in a 1D tensor, and then to compute the overall length, you would sum over the tensor and then call item to get out that length. You could then use this sum to allocate a new tensor with enough space to store all of the packed sequences contiguously in memory. From a framework perspective, we don't know anything about lengths. It could be anything. Its sum could be negative for all I know. But when you take its sum and pass it to a tensor constructor, we can infer that it must be greater than or equal to 0, because if it wasn't, then torch.empty would error. We can then use this fact to resolve other questions we might have about L, like if someone writes an if statement on L is greater than or equal to 0. Of course, it is possible for a user to pass in a tensor that would cause this model to error at runtime. So in our generated code, we generate runtime asserts checking that these assumptions are correct. So here's a real-world example of this principle in action. In recommendation models, it's common to implement model parallelism by distributing your large embedding tables on multiple nodes. At the beginning of your training process, you'll start with data parallel batches of feature indices, some of which may be on the wrong node to actually do the lookup. You have an all-to-all collective to send the features to the right node so you can do the embedding lookup where the embedding table is. This collective actually has to be done in 2 steps. The number of embedding lookups you do on each node is dynamic. While you're going to want to design your sharding so it's as balanced as possible, which features are actually going to show up on the users is highly data dependent. So you first have to do a small all-to-all communication saying how many elements should each node expect to receive before you actually send the tensor data itself. In TorchRec, the first communication is done by this all-to-all splits implementation. The important part of the code is below after we receive the data from all the hosts. We immediately go ahead and call toList on the tensor saying, hey, give me a bunch of Python integers. And we're just going to go ahead and do that, use these to actually create the output tensors that are going to receive the real output data. So with inferred runtime asserts, this actually just all works without any user annotations. One more thing. Previously, I said that when you pass L to torch.empty, we would infer that L is greater than or equal to 0. Well, I lied. Remember 0 and 1 specialization? If we only infer that an argument to a tensor constructor is greater than or equal to 0, chances are we would still hit some framework code that we would want to know if L was 0 or 1. So we have special handling for size-like uses. We will immediately assume that L is greater than or equal to 2 at compile time. But at runtime, our generated runtime assert will only test if L is greater than or equal to 0. This is the same principle as unsound 0-1 specialization and export. And like before, you can technically write user code that violates this assumption. So beware. And we're using this to good effect on things like keyed jagged tensor, also a thing from TorchRec, which represents sparse features from users. Due to sparsity, many features will often only have 0 or 1 elements in them. If you 0-1 specialize them, you will spend forever recompiling as, this feature is 0, now that feature is 0. If we use unbacked syments, which are assumed to be greater than or equal to 2, we can just generate a single compile product that works for any sparsity pattern. So there's a lot more going on under the hood with dynamic shapes, but these are the main things that I wanted to tell you about today. Where are we going with dynamic shapes in 2024? Well, the big thing is we need to keep fixing bugs. There are still lots and lots of bugs. I know Sumit told us to be gentle with PyTorch 2 when we first released it. We're working on it. The good thing is that most bugs these days are shallow. They're actually pretty easy to fix. So just send us bug reports, and I promise you within a few weeks, someone like me is going to get around to it. And they're usually small fixes. The other focuses we have, one of them is on data-dependent operations. We're really been working hard on it, and we're going to keep working hard on this. We want out-of-the-box recipes for the common patterns. We're also investing a lot on recommendation systems because I do work at Meta. This is kind of one of the things we do a lot of, and jagged layout is another thing. Not only just being able to trace it, but also to generate good code. And of course, I would love the performance of dynamic shapes to get better, and to do that, we need to have more smarts at inductor runtime so that we can actually do those things. So I had a bonus slide, but we're out of time, so I'm just going to leave it here. Thank you, everyone, for listening. Any questions? Yes. That's a great question. So the question was, in PyTorch core, do we use Torch compile to implement eager operators? And if not, what remains to be done? So the answer is no, we don't, except for I've got an implementation of a CRC hash that uses XOR sum. It's kind of janky, but that's it, and it isn't used for anything. And the main barrier to doing this, so historically it was dynamic shapes, but we're doing pretty good for dynamic shapes these days. So the other problem is just compile time overhead, because right now we always recompile every time you launch your Python process. And for something like in the eager framework, you don't, the whole point is to have a bunch of pre-compiled stuff. So the compile cache that Mark Serafine talked about does help a lot here, but we need to make this experience a lot better before we can start actually replacing things in PyTorch eager this way. Other questions? Yes. Well, I mean, in this particular case, okay, the question is, how do I know what to compile in this example? And I think I misunderstood, but the torch compile annotation tells me which parts of my program to compile. So I'm not compiling the 3 calls to F because that's not under torch compile. Does that answer the question? Yes, I don't recompile because I have a dynamic kernel now. So there's a question which is, what if I called F with a really big shape? Would my kernel work on it in that case? Okay, so the naive answer is, well, we build a kernel that works for any size, so this can't happen because it works for any size. Actually, that's a lie, because there's this thing called 32-bit indexing, which makes your compute a lot faster. And so we actually the reason that's the reason why this example has backend AOT eager on it. If you actually send it to inductor, you're going to get a bunch of these extra guards about being small enough to fit within a 32-bit address. So if you have something too big, you'll need a separate kernel for that. And that's the kind of thing that will happen in inductor when we decide it's worth it. Yeah, so the question is, what is backend AOT eager? So AOT eager is, so if you remember, the way PyTorch 2 works is there's Dynamo, then there's AOT autograd, and then there's inductor. So you can swap out these pieces. So if you run only Dynamo and AOT autograd, but you don't run the actual backend code gen from inductor, that gives you AOT eager. So it's useful for debugging because there's this big code gen step that you can just run eager instead in that case. Okay, I think I am officially out of time. Is that right, AV folks? Okay, thanks everyone.